Now we get to this case we need to answer, all right? Does not exist. But we want to compare how the method is using upper bounds and lower bounds for comparison. Upper bounds, lower bounds. When you see upper bounds, lower bounds, in your mind, you can imagine the basic mathematical tool we use, inequality. How do you do the upper bound, lower bound calculation? Using inequalities. Here, we use a lot of inequalities. Yeah. All right. How? Yeah. The function g of n is usually a simple function. Yeah, g of n, growth function. Remember, how do we get growth function? We try to make it as simple as possible, right? We take the dominant term, then we remove the constant, or we just use the leading coefficient at 1. Yeah, we try to simplify it as much as we can. Yeah. So like n squared, n log n. So that's our typical GL function. Typical situation. But here I use usually. Usually means most of the time, but not 100%, right? Sometimes we do not have to take g of n as a simple function. Could be a complex function. It's okay sometimes, but it's rare. Yeah. We allow it, but in the real world applications, we rarely see that case. We rarely see that kind of case. Only theoretically on paper, when we do the math, we will handle that case. But in the real world, we rarely work on that case. Yeah. All right. The function f of n could be a complex function. Yeah, typically it's a relatively more complex function. Use some constant multiples of f of n, g of n to approximate f of n. Yeah, here. The third point is the main point about this method, using upper bounds, lower bound. That method, the main point for this method. Yeah. How do we set upper bounds, lower bounds for this f of n function? It tells us the way to set those bounds. What way? Using some constant multiples of g. Yeah, that's the typical way. Constant multiple of g. Yeah, so that will make this method a little easier. So we know what we should do. Yeah, the third point tells us. Yeah. All right, specifically, can we find two positive constants, C1, C2, such that C2 times g of n less than or equal to f of n less than or equal to C1 times g of n condition. Yeah. This inequality holds under certain condition. Yeah. But later we will really study that condition. Yeah. So here we just put it on hold. The condition is missing at this point. Yeah. We will come back to fix that problem. Yeah. So now you can see, because if we use inequalities, we never do the limit calculation. We never do the limit calculation. Okay? So in this case, even if the limit does not exist, we can still use the inequality way to do the comparison. All right? Inequality way to do the comparison. Yeah. We don't have to stick to that limit method. Yeah. All right. So two methods. You can see inequality method and a limit method. Yeah. All right. Now, big O notation. Yeah, here I talk about our fourth. Yeah, little o. Yeah, we talk about, but here big O. All right, big O notation. What's the big O notation? Big O notation, because after we introduce this inequality method, now we are ready to talk about other related asymptotic notations. Okay, yeah, big O notation. For a given function g of n, the notation big O of g of n, this time, represents the set of functions f of n that satisfy the following condition. There exists some positive constant c, and now I try to address the missing condition there. Yeah, missing condition there. Yeah. Some non-negative integer and 0 such that f of n less than equal to c times g of n. This inequality holds when n greater or equal to that n 0. That is the missing condition. All right. Yeah. That means, we know n means the problem size. Usually we say when the problem size is greater or equal to some fixed constant number, n0, some fixed constant number. Greater than that, passing that line, then we have the inequality. Before this line, we do not require that inequality. Okay? We do not require it. Yeah. Only after that line, the inequality is true, then we have the big O notation. Okay? Yeah. I hope you understand the subtle meaning here. Yeah. Yeah, pretty subtle. Yeah. All right. Yeah. And in our wording later, in many of my questions, when I talk about this condition, I will say when the problem size n is sufficiently large. Okay? The wording regarding this condition, we usually say when the problem size n is sufficiently large. Yeah, because in the real world, when you say when something is sufficiently large, people may ask you, what do you really mean sufficiently large? Right? Because it is very vague. Very vague. In different people's mind, the sufficiently large could be different. Okay? Yeah, for example, do you mean 100 is sufficiently large? Or 1 million is sufficiently large? Or 1 billion is sufficient? Can you say that? Yeah. You cannot, right? Because with respect to particular problem, for some problem, 100 is sufficiently large. For some question, 100 is sufficiently large. But for some other problem, 1 million is not sufficiently large. How about that? Okay? Yeah? So that's why this something kind of relativity theory, right? Some relativity thinking here. Yeah. So let me give you a simple example here. Yeah. If you look at this, yeah. Parenthesis n minus 20 to 4. How about that? Yeah. Look at that function. F of n equals parenthesis n minus 20 to the 4th power. For this case, is 100 sufficiently large? Yeah, 100 minus 20, positive. Yeah, So you can use a, positive power function for f of n, right? Yeah. So look at that. So because 20 already sufficient. A number greater than 20 already sufficiently large. Yeah. You pass some fixed constant number. That fixed constant number is 20 here. All right. Yeah. All right. Next, if I n minus 10 to the 7th power to the 4th. Yeah. When we look at that, all right, 1 million is not sufficiently large, right? Yeah, 1 million, because 1 million 10 to the 6th, all right? Here we have n you need to minus 10 to the 7th, 10 million. So 1 million not sufficiently large because you cannot overcome this, negative constant. Yeah. So that's why I say, if you look at the specific value, you cannot say if it is sufficiently large or not. You need to look at the specific function to tell you if it is sufficiently large, right? Yeah. So try to understand, the subtlety here. Yeah. All right. Now, based on this, I will create some comprehension questions related to this point, yeah, to check your understanding. Yeah. All right. So let's continue. Yeah. All right. Yeah. So that little n0 plays an important role. Okay? Yeah. So, all right. Yeah. And here, let me talk about this little n0 a little bit. Yeah. Here, yeah. When we select little n0, in that example, we can select 20. This example, we select 10 to the 7th. Okay? Yeah. So when we select, that means we have freedom to select, right? Yeah. So 20 there, 10 to the 7th here. We have some freedom to select n0. Yeah. But in your problem, as soon as you select it, you need to fix it. Okay? Give you freedom to make selection. As soon as you make your selection, stick with it. Do not change. Do not change when n goes to infinity. You never change when n goes to infinity, right? After you select n0, fix it. Then, we make n goes to infinity, you have that inequality. That's the exact meaning for that n0. You have freedom, but there is limitation, rule for you. You do not have unlimited freedom, okay? So you have limited freedom. Yeah. You make your choice at the beginning. Yeah. When you feel, but you have to do the math to tell you if that is sufficient or not. Yeah. If not sufficient, you may get trouble, right? You have to make sure it is sufficient. All right? Then you stick with it. When n goes to infinity, you always stick with it. That's the meaning of n0. Yeah. All right. Yeah. So later, I hope when I talk about n is sufficiently large, you will not ask me what's the meaning of that, because that's the whole story. Yeah. We spend a lot of time for that story. Yeah. Because if you ask me to explain it, I may need to spend half an hour, right? So I don't want to every time go through that half an hour. Yeah. Yeah. No, sorry. Yeah. Yeah. Something is wrong here. Yeah, let me fix it at a break time. Yeah. All right. Next,